Okay, so now we've investigated the states of well-defined momentum, which, as you recall, were these plane waves with a wave number p upon momentum upon h bar. We can go back to this problem of two-slit interference and ask ourselves why it is that quantum interference isn't observed in macroscopic objects, and also assess what experimental setup would be required to see quantum interference with, say, electrons. So we can put some numbers into this experiment. So as you recall, we had some gun here that was symmetrically placed with respect to a couple of slits here in an obscuring screen. It fired out particles. Some of the particles got through the holes, and they came to here, and we said that the amplitude up here would be the sum of the quantum amplitude to arrive at this point would be the sum of the amplitude to go via this route or to go via this route. These routes, well, the distance from the gun to the two slits by setup is symmetrical, is equal. So any difference in the amplitude that they come there is to do with the change in the amplitude when it goes along this route as against along this route. So let d plus be the distance from the upper slit to this place, and d minus the distance to the lower slit. Then we can write a formula that d plus by Pythagoras' theorem is going to be L squared plus x minus s squared square root, and correspondingly d minus is going to be the square root of L squared plus x plus s squared. And we make the reasonable conjecture. I mean, the right way to think about this is these particles, let's imagine that we've got our gun here has been tuned to emit particles with some well-defined energy. That means that as they go along here, the particles will have some reasonably well-defined momentum because their energy will consist of their kinetic energy. So along here, we will have that the amplitude is going to be on the order of e to the I p upon h bar times x. So that's a reasonable model for how the amplitude varies with position. That's the new information that we bring to bear on this. So what will be the difference? So the probability to arrive at x, as you recalled, was equal to the amplitude to arrive by the top slot plus the amplitude to arrive at the bottom slot, mod squared, and the argument that this was a plus mod squared plus a minus mod squared plus twice the real part of a plus a minus. And these were about equal, and, well, these were the classical probabilities. So these were p plus p minus, and then we have this quantum interference term, which we want to assess. So what is this quantum interference term? So the interference term is going to be mod A plus, mod A minus, not very interesting. And the crucial thing is that this one is going to be e to the I p upon h bar d plus, and the other one's going to be e to the minus I p upon h bar, plus. One of these needs to have a star in it, which means that one of these acquires a minus sign. So we're interested, in the real part of this. And the real part, so this thing can be written as cos p upon h bar d plus, d minus minus d plus, et cetera, et cetera, et cetera. So this is looking like the probability to go either way times through each hole separately times the cosine of p over h bar d plus minus d minus. Actually, it's easier to do it the other way around, isn't it? Minus plus. So what is this difference of distances? This difference of distances from up there. Well, let's binomial expand this, and because we can argue that L is going to be big experimentally compared to X. X will be millimeters, L will be a meter or so. So we can binomial expand this and say that this is L. It's about half of L, brackets 1 plus X minus S squared over L squared plus dot, dot, dot. And the other one's going to be about half L 1 plus X plus S squared over L squared plus dot, dot, dot. So when we take the difference of those two, so this is going to be 2p plus minus this probability times the cosine of p upon h bar of the difference is going to be x plus s squared over L minus x minus s squared over 2L, in fact. So when you take the difference of those two, you will be looking at 2 xs over L yes, 2xs over L is what that difference will be. So now let's put it. Now we need to put in some numbers, right? Suppose we take the energy, which is p squared over 2m. What do we want to do? We want to. No. So what does this do? This gives us a probability of arrival as a function of x, which is going to consist of of twice the sum of these two, which are going to be about equal, and so about twice this, plus twice this thing times this cosine. So it's going to be an oscillating commodity, which will be doing this, and there's some characteristic distance between these minima, which, so this, we'll call this delta x, say. No, let's call it big X. I think that's what so we'll call this big X, the distance between the places where it's a minimum, because the quantum interference term is cancelling the classical term. And this difference is what causes the argument of that cosine to become 2 pi. So we can write that 2 pi is equal to p over h bar times 2s over L times x. In other words, we have a formula for the distance between the minima, which is 2 pi h bar, but h bar is h Planck's constant over 2 pi, so that's going to be h over p hl, sorry, yes, of s. Yeah. And we could also write this, I guess, we could also say that, oh no, let's not bother. So let's put some numbers in. Let's say that E, the energy, is, so in order to get a big value of X, we want to take a big value of L, needless to say. We want to take a small value of P, and of course a small value of S.
Another 2 on the bottom of that?
I've lost a 2, yeah, you're quite right. So let's take L to be a meter. Let's take S to be I think. What did I do? I think it's yeah, a micron. Because you want to make it as small as you can, but if you make it much smaller than a micron, you'll find it difficult to make the whole. Using ordinary materials, and we also, in order to get a small value of P, we want to take a small value of the energy, but you can't take too small a value of the energy, or your particles will be deflected by stray electromagnetic fields and stuff, and it'll be difficult to keep any kind of coherence. So let's take 100 eV, say, as a sort of convenient low speed. If you plug all this stuff into there, so that gives you, what does it give you? 20th of a millimeter or something. I think it's, is it 0.06 millimeters? Which is obviously perfectly observable. Yeah. So this such an interference experiment is possible but hard using electrons. If you do the same thing with bullets, when we're not expecting anything to happen, what could we do? We would take the velocity from a gun is, say, 300 meters a second. It might be a bit faster these days, I'm not sure, but that's a classical, that's faster than sound, so that's sort of a reasonable ballpark figure. Suppose we took L to be 1 kilometer, 1,000 yards, pretty reasonable shooting distance for a rifle. And if we took the mass to be 10 grams, put it into the same formula, and we discover that x is some ridiculous figure, 10 to the minus 29 meters. So it's obvious that you cannot observe this interference using anything like a bullet, any kind of macroscopic object, because it's going to be vastly bigger itself than the size of the interference pattern. Obviously, an absolutely basic requirement for this experiment to work is that the physical size of your particle has to be smaller than the value of x that you derive out of this, so you haven't a hope of measuring this interference. So that's why classically we're unaware of this interference term, but I would remind you that in the last lecture we recovered classical results which explain why cricket balls move as they do, why satellites and so on move as they do, by interpreting, we calculated this, we obtained results which recovered classical physics by decomposing the amplitude to arrive into a sum of contributions from states of different well-defined momentum, and these were all interfering with each other, and the classical physics came back as a result of quantum interference. So this quantum interference, on the one hand, is something which is very hard to observe with classical objects. On the other hand, our entire picture of the classical world is only recovered through quantum interference. It's not some esoteric corner of the subject, but it is hard to it's hard to have it happen in a controlled way. Okay, so we should just so we've done the position representation in just one dimension. Everything has been one-dimensional motion along x. We obviously need to generalize the position representation to 3 dimensions because we live in a 3-dimensional world for whatever reason. And the generalization is nice and trivial. We don't need to worry about it. We now have 3 position operators, x, y, and z, also known as xi, all right? And we have, of course, 3 momentum operators, 3 more operators, px, py, and pz, also known as pi. And we have that every one of these operators commutes with the other one. So we have that xi, comma, xj is nothing, and every one of the momentum operators commutes, pi, comma, pj equals nothing. So it is possible to simultaneously know your x coordinate, your y coordinate, and your z coordinate. There's a complete set of eigenstates, of well-defined states where you know all those 3 simultaneously, or you can know all 3 components of momentum, but you can't know, there's not a complete set of states for knowing, and so on. And the only other interesting thing we have to have is xi commuted with pj is IH bar delta ij. So it is possible to know the x position and the y momentum, but it's not possible to know the x position and the x momentum. So most of these operators commute with, well, each operator commutes with 4 of the remaining 5 operators, but it does not commute with its own momentum. That's what each of these position operators. So that's the generalization there. What else do we have to say? Well, we used to have a wave function of psi being a function of scalar x. We now, it's trivial, the argument of the wave, we can now label a complete set of states by x, y, and z. So we can write that we have states of well-defined position which are labeled by a vector now, vector position x, because there are three. This is an eigenstate of the x operator, it's an eigenstate of the y operator, and an eigenstate of the z operator. So we need three eigenvalues written inside here to describe what this is. That's at a mathematical level. At a physical level, this is the state of being at the location position vector x. Correspondingly, our wave functions become functions of x, y, and z because they become these complex numbers. Right? That's still a complex number, this complex number, but it's a function of x and y and z, the locations of the particles. Similarly, we have states of well-defined momentum, up. We have states, up of x, which is x, p. So now here we have px, py, and pz because we have a state of well-defined momentum which is labeled with all three components of momentum. So we have this function of a complex of this complex function of three variables, x, y, and z, labeled by the momentum. This is just an identical notation. And whereas in when we were doing this in one dimension, we found that this was e to the I p over h bar times x, not vectored. Now that's a vector, and whereas on the bottom we used to have h bar to the 1/2, now we have h bar to the 3/2, reflecting the fact that there's an x component to this, a y component to this, and a z component to this. So this wave function of a state of well-defined momentum has now become a plane wave whose wave surfaces are normal to the vector p, and that's what it is. It's easy to check that stuff works. It's a very straightforward generalization of what we did before. And I think that's all we have to say. Oh, not quite. We also want to say what the momentum operator p looks like. So previously we had that xp, sorry, it's not what I'm talking about. Yeah. xp of psi was minus ih bar. It was introduced by this formula here, d by dx of x of psi. All right? That was what we did in one dimension. That generalizes in three dimensions very straightforwardly to x p psi. So that's become a vector. That's become a vector because we have to write down what it is for px, py, and pz. This is really going to be a shorthand for three formulae. And it's going to be minus ih bar gradient operator on the function of three variables, function on space, this one here, right? The wave function. So this is a vector reflecting the fact that that's a vector. This is just a label which appears on both sides of the equation. That's what this formula generalizes to that formula. I don't think we need to be detained about that any longer. Before we leave the position representation, it's good to do a useful result, which falls into our laps now because of work we've already done, called the Virial theorem, which is a theorem. It's a result in classical physics which you may not have met, I don't know, but you in a way should have met. Did you cover the Virial theorem in classical mechanics anywhere? No, anyway. So there's nothing quantum mechanical about the Virial theorem. It has a classical counterpart, but it's going to fall into our laps because we've got this powerful machinery. So do you recall, if we are in a stationary state, that is to say a state in which the result of measuring energy is certain, then all expectation values for such a state are constants. That's why we call it a stationary state. It's going nowhere. So every expectation value for a stationary state, for a state of well-defined energy, is independent of time. So we want to exploit that result. So for a stationary state, this is just recalling what we already had. It was a consequence of Ehrenfest's theorem. For a stationary state, we have that d/d time, or even d/d time of E Q E equals naught for all operators Q. It doesn't matter what observable you stuff in there, as long as the observable is defined in a way that's independent of time. So it's something like position, momentum, angular momentum, whatever. It has a vanishing rate of change with respect to time. It's a constant. So we now apply this result to Q is equal to X dot P. So then we have that naught is equal to d/dt sorry, sudden moment of doubt. Yeah. So I want to apply this to x dot p e, and let's divide sticky in our h bar. That, by Ehrenfest's theorem, is x dot p comma h. Whoops. So Ehrenfest's theorem tells us that this rate of change, which vanishes, is equal to this here. And now let's take, suppose we're dealing with a particle which has kinetic energy and potential energy. So we'll take the Hamiltonian to be of that form, which is a pretty useful form, and stuff it in there, and we're going to have that naught is equal to E x dot p comma p squared over 2m plus v, close square brackets. So now we need to work out what this commutator is, and this is where this is where we get a bit of practice in using the three-dimensional generalization. We obviously have two things to work out. We've got a commutator of x comma p with p squared. So let's work that out. X comma p with p squared. Now we write that in components. We write x dot p, sorry, x dot p. Did I say comma? X dot p comma p squared. This x dot can be written as a sum over j equals 1 to 3 of xj, pj. So that's just a way of writing that. And now I have a sum pk, well, p squared k. So now I'm summing over k as well. Right? P squared is px squared plus py squared plus pz squared. Now we can work out this using our rules for a commutator. We had that rule that ab comma c was equal to a comma c b plus a b comma c. P, we know that pk commutes with pj. That's been written down up there. So that commutator vanishes. That's this one here in some sense. That's this one here in some sense. And so what we're left with is, so we have this double sum. We're going to have xj pk pj, sorry, that's squared, comma, no comma. So that's what we get. So this has to be commuted with that. That's what I've written down, I hope. And then there should, in principle, be another term, this commuting with this, but that vanishes because pj commutes with pk for all j and k. So we have to work out what this one is now. And we can use the same rule if we're being pedantic. We would say this is x on pk, pk. So we would say that this is xj, pk, pk plus pk, the commutator of x and pk. I'm using the same rule, and that all has to be multiplied by pj. The same, because I'm now writing p squared as pk, pk. But this is IH bar, this is IH bar, so these two terms actually contribute the same thing. This becomes 2 IH bar p times delta jk times pk times pj. And I'm sorry, I've lost track of the sum sign. Here we have a sum sign. We're summing over j and we're summing over k. Sum over j, and you get nothing because of this delta jk unless j is equal to k. So this becomes pk, pk summed over k. But pk, pk summed over k is the same thing as p squared. So this is 2i h bar p squared. That's what the commutator is of x dot p with p squared. Now let's do the x dot p commutator with v, which is itself a function of x, of course. These things all ought to have hats, really, but it's difficult to write down enough things. Well, what we want to do is write this thoroughly in the position representation. In the position representation, x dot p is minus I h bar x dot gradient. Right? That's what this becomes in the position representation on v, which becomes a function of x. So this is in the position representation. So what does that mean? That means IH bar minus IH bar brackets x dot gradient working on v minus v x dot gradient. And this is an operator statement, so it's waiting for you to put in the function of your choice of psi on the right? There's a virtual function there for it to work on. That's the meaning of this v x dot gradient. And this x dot gradient v doesn't mean x dot gradient only v, it means of everything that is to the right of it, including your psi. So when you use this x dot v on v times alone, you'll get a term, and then you will still have to use the x dot v on the psi, but the result of using the x dot v on the psi will be killed by here, an x dot v on psi. So what this is equal to is minus IH bar x dot gradient of v. That's all that survives this, is the action of the nabla, the gradient operator, on the potential itself. The action of the gradient operator on the wave function that's virtually sitting here is cancelled by this contribution here. So we now have, we can put these results back into what we had up there. So what we had was naught is equal to, is equal to the sum of these commutators is equal to E x dot p comma p squared E plus E x dot p v. That's just summarizing where we stand. This we've discovered to be, this is 2i h bar. This commutator turned out to be p squared, so it becomes the expectation. Oops, there should have been over 2m on this, shouldn't there? Because it was the Hamiltonian, p squared over 2m. This p came from the Hamiltonian where it was p squared over 2m. This v came from the Hamiltonian where it was just v. So we have over 2m, no, let's leave that alone, of p squared over 2m, e plus, we figured out that this one was a minus IH bar so we want to cancel what this is the expectation value of the kinetic energy, clearly, right? P squared over 2m is the kinetic energy. This is the expectation value of it. Cancelling the IH bar, we can say that 2 times the expectation value of the kinetic energy is equal to this stuff. That's as far as we can go in general. But consider now, very important cases have that V of x is proportional to mod x to the alpha. So for example, for a simple harmonic oscillator we're about to discuss, the potential energy goes like x squared, alpha's 2. If we were dealing with the Coulomb interaction, the potential energy goes like 1 over radius. So it would be V of r is proportional to 1 over r. Well, this mod x is r. So alpha would be minus 1. So we can say that alpha equals 2 is simple harmonic motion. Alpha equals minus 1 is Coulomb. There are, you can think of other power laws which are relevant. In this case, so then, if we ask ourselves, what is x dot gradient of v? Well, that's going to be, so we'll say that this is equal to some constant a times x to the alpha. What is this going to be? It's going to be alpha mod x to the alpha minus 1 times x dot the gradient of mod x. And the gradient of mod x is x, the unit vector x, so it's the vector x over mod x. So this is equal to, this is a. We have a x to the alpha minus 1 times x dot x over mod x. So here, this mod x is going to make this an alpha to the minus 2, but from this x dot x, we're going to get a mod x squared. So this is going to be, and I've lost, this was an alpha. There was also an a, unfortunately. We need an a and an alpha. This is going to be alpha times a x to the alpha, which is alpha times v. So if v has a power law dependence on distance from the origin, then x dot grad v is simply alpha times v. So when we put this result back into that formula, back into this statement here, we have that twice the KE, expectation value, is equal to alpha times the expectation value of the potential energy. So that's our Kepler formula. In the case of simple harmonic motion, alpha is 2 and kinetic energy is equal to potential energy. In the case of Coulomb interaction, where alpha is minus 1, you have that the potential energy is minus twice the kinetic energy, which is to say that the particle has lost 2 units of energy in falling in from infinity into a bound orbit. It's lost 2 units of energy. 1 unit's been sent off to infinity in radiation or something, and 1 unit is used as kinetic energy of its orbit. So this is the Virial theorem. So now we open a new chapter, as it were, by talking about harmonic motion. The harmonic oscillator is the single most important dynamical system in physics. most of field theory, most of quantum field theory, most of condensed matter physics is fiddling with more or less with harmonic oscillators, which are decorated in some way. So the basic physics is that of the harmonic oscillator, and it's worth just taking a moment to understand why harmonic oscillators are all over the place. The universe, physicists, a fundamental position of physicists, well, physicists like to represent the universe as a collection of harmonic oscillators. And this is partly because physicists are maybe brighter than some other people, but they're still pretty stupid. We have quite a small bag of tricks. And a harmonic oscillator is a trick that we have, and it's an incredibly useful trick for this reason, that if you plot force in some direction versus displacement from a point of equilibrium, you will get a curve which does something like this. The force vanishes at an equilibrium. At a point of equilibrium of a system, the force on it obviously vanishes. So if you do a plot of force versus distance, you'll get a curve something like this, passing through 0 at the point of equilibrium, which I happen to have put at the origin of x. But, you know, that's by construction, clearly. And the general idea is that most of the time, you can sorry, that's meant to go through the origin. Most of the time, you can represent this to a good approximation. You can say that f of x is about equal to kx plus order of x squared or whatever. So to lowest order approximation, because f has to vanish at a point of equilibrium, in the neighborhood of the point of equilibrium, f is going to be proportional to x. And if we neglect this, if this is small, then we have harmonic motion for displacements, these small displacements around here. So this is why harmonic oscillators are ubiquitous, an incredibly valuable model we can use to understand many, many systems, because many systems for small displacements, almost all systems for small displacements, look like a harmonic oscillator. Okay, so let's agree what the Hamiltonian of this thing should be. The Hamiltonian of our harmonic oscillator should be p squared over 2m plus a half k x squared, right? Because if the force is going like that, you integrate it up, this becomes the potential energy, and this is, of course, the kinetic energy. We're familiar with that already. It's better, though, to write this in a different way to anticipate results that are to come, and to write this as p squared plus m omega x squared over 2m. So, and of course, omega squared is k over m. So it's easy, defining omega squared to be k over m, it's easy to write this formula like that, and that's how I want to write it. If you want to reproduce this formula, just think about dimensional analysis. We want to have p squared over 2m because it's the kinetic energy. We're always saying that. And here, I want something that's proportional to x squared and has the dimensions of momentum. And obviously, omega x has dimensions of speed, so m omega x has dimensions of momentum. So that's why, you know, that enables you to recover that quickly from this. And that's the way to go for practical purposes. So there's our Hamiltonian. And we're trying, of course, to solve these stationary states are the key to understanding dynamics because they have this trivial time evolution. And by decomposing any initial condition into a sum of stationary states, into a linear superposition of stationary states, then evolving the stationary states, we find out how any arbitrary initial condition evolves in time. So that's why we want these stationary states. I've said that before, and I'll say that again. So we want to find states of well-defined energy. This is the problem we want to solve. And this is a completely generic situation in physics. First of all, you think about your physical system. On the grounds of physics, you write down the Hamiltonian. Then the next thing you do is you find the damn stationary states, because once you've got those, you can do anything you want, pretty much. So that's what we're trying to solve. The way to do this is the proper way to find these states. So we need to find the energies that are possible, and we need to find the corresponding states. And the way to do this is to introduce some new operators. Let's introduce A, which is m omega x plus I p over the square root of 2m omega or h bar omega. Why do I write that down? Well, basically because I know where I'm going, but just to give you some sense of direction. The general idea here is that we want to factorize that. That's the general idea. We want to factorize the Hamiltonian into, it's a quadratic expression. It seems kind of reasonable to factorize it. If these weren't operators, because these are operators, sorry, and in future I'm not going to even attempt to put hats on operators, right? These are operators despite the absence of hats. It's just too difficult to remember to put the hats on and takes too much time, and grown-ups never do. But these are operators. Now, if they weren't operators, this and its complex conjugate would factorize that. So that's the drift, okay? Let's write down its complex. This, of course, is an operator, and it's not an observable. It's not a Hermitian operator. What is its dagger? A dagger, its Hermitian adjoint, is this thing dagger, which is itself, because x is a Hermitian operator on its own dagger, so it's m omega x, plus this thing dagger. P is its own dagger, but I has the dagger of I, the Hermitian adjoint of I is minus I, so this is minus I p over, of course, this on the bottom is a real number, so it's its own complex conjugate. So here we have two operators, and the general idea is they're going to factorize h, or they almost do, whatever. That's the plan. And this is called an annihilation operator. And this is a creation operator. And the reason they have these names will emerge, but it is that if you use this on a state, this operator increases the excitation of our harmonic oscillator, and this oscillator reduces the excitation of our harmonic oscillator. And since in quantum field theory particles are excitations of the vacuum, this thing creates a particle because it creates an excitation, which is a particle, and this thing destroys a particle because it destroys an excitation. So what we next do is work out what A dagger A is, because the idea was that this product would be more or less the Hamiltonian. So what exactly is it? Let's get this right. M omega x minus IP, M omega x plus IP over 2m h bar omega. Now when we write this out, we have the obvious terms. We have p squared, and we have m omega x squared. So let's write those down. That's p squared plus m omega x squared all over 2m h bar omega, 2m omega h bar, whatever. And then we have some additional terms which would cancel in classical algebra but don't now, because we have an x, we have an m omega x times ip, and here we have an m omega x on the, sorry, have a minus ip times an m omega x. So the additional term is an m omega x, m omega I x comma p. And it's again over 2m h bar omega. Right? So this is the Hamiltonian over h bar omega. And this is an IH bar, and the i's make a -1 with this, so this is going to be minus a half, and everything else will cancel. Right? Because we've got an m omega here, and we're going to get an h bar from there, so the rest cancels. So I should have explained, sorry, I wanted to factorize this, and this on the bottom, this normalizing factor on the bottom is put in. It's not really essential, but it's very convenient, and it's put in order to make this dimensionless. So just to check that that's true, h bar has dimensions of position times momentum. Right? So it has the dimensions of position times momentum. So what we have here is m omega x, which we've agreed has dimensions of momentum, times p, which has dimensions of momentum. Then we take the square root. So this on the bottom has dimensions of the whole square root of momentum, and therefore cancel the dimensions of what's on the top. So it's dimensionless. That's the purpose of the horrible square root. So we find that this product, which is dimensionless, is equal to the Hamiltonian divided by h bar omega, which has the dimensions of energy, because h bar also has the dimensions of energy times time. Omega, of course, has dimensions of 1 over time. It's the frequency of the oscillator. So this has dimensions of energy minus a half, which is obviously dimensionless. So we have indeed almost factorized. We have the statement now that h can be written as h bar omega, which carries the dimensions, times a dagger a plus a half. We've almost factorized h. Just there's that there. The next thing we want to do is calculate the commutator a dagger comma a. Yes, we've just got time to do this. A dagger a of these two operators. So, of course, we will have a 1 over 2 m h bar omega as a factor on the bottom, because each of these a's brings in its own square root. And then we will have the commutator of m omega x minus ip on m omega x plus ip. Now, we have, this breaks down into 4 commutators in principle. There's the commutator of this with this, and the commutator of this with this. The commutator of this with this obviously vanishes because x commutes with itself. And the commutator of this with this is so we're going to have an m omega I times x comma p. That's the commutator of this with this. And now we have to deal with these terms. This produces a non-negligible commutator with that. We're going to have minus m omega I times p comma x. And then we'll have the commutator of p with self, which will vanish. If I swap those two over, then clearly I change the sign in front, and then this becomes a plus x comma p. It becomes this thing all over, so that cancels this, and this whole caboodle is going to equal I x comma p over h bar, because we're going to get a 2. These two terms are going to add together to make us a 2, which cancels with this, and the m omegas clearly go. X comma p is itself equal to I h bar, so the i's make a minus 1, the h bars cancel, and this is equal to minus 1. So these two operators have non-vanishing commutator actually equal to minus 1. Yeah, well, we seem to still have time to nail this problem, I think. So let us suppose we have got a state of a stationary state. Let us now apply the operator a dagger to both sides of this equation, right? Then this is just an eigenvalue. It's only a number, so I can then write e a dagger e is equal to a dagger h e. That's obvious. I would like to swap these over, so I jolly well do. I say this is equal to h a dagger plus a dagger commutator h. So this commutator puts in what I'm supposed to have and takes away what I'm not supposed to have but have previously written down. But we know what h is in terms, we have that h is equal to, there it is, h bar omega a dagger a, so let's use that. So this is h a dagger plus commutator of a dagger, and h turns out to be a dagger a plus a half, close brackets, h bar omega to carry the dimensions, close that, and stick in our e that we first thought of. So all I have done is replace h by an expression we already derived. Yeah. Now I have to take the commutator of a dagger with this and with this. The commutator of A dagger with a half clearly vanishes because a half is just a number, not an operator. The commutator of A dagger with itself vanishes. So when we do the commutator with this product, there should in principle be two terms, but only one of them survives, and that term is this stands idly by while the A dagger works on that. And then I have an h bar omega, close brackets, E. But we just worked this thing out and found that it's -1, right? A dagger A turned out to be -1, so this is equal to H A dagger E minus H bar omega A dagger E. Just to remind us what we had on the left was E A dagger E. This is just a restatement of what's been at the top. So we take this A dagger E and we obviously join it onto that A dagger E, and we discover that H on A dagger E is equal to H working on this, the ket that you get by using A dagger on E, is equal to E plus H bar omega of A dagger working on E. What does this tell us? It tells us that we have, out of a state which had energy E, we have constructed a state by multiplying by A dagger which has energy E plus H bar omega. So this means that A dagger E is equal to a constant, normalizing constant not discussed, times E plus H bar omega, a new stationary state. And this is an incredibly powerful result because it immediately follows that we have states. If we can find a state E, we can immediately generate E plus H bar omega by using this A dagger beast. And also, if we use A dagger on this, it follows we're going to get E plus 2 H bar omega. And we're going to get another, if we use A dagger on this, we're going to get E plus 3 H bar omega. So we're going to get a whole infinite series of states of ever-increasing energy simply by applying A dagger again and again and again. So what remains is to find what number E is, and that we will do first thing tomorrow.